In the deepest months of a Nordic winter, when the sun disappears and the cold cuts through bone, early northern builders faced a problem that should have been unsolvable. How do you heat a home in a world with almost no wood, no stone, and temperatures that plunge to 40 degrees? Fire alone wasn't enough. Fuel was scarce, smoke was deadly, and any heat you created vanished into the frozen air within minutes. Yet somehow, these Arctic engineers built shelters that stayed warm, using nothing more than snow, ice, and the movement of air itself. Their solution wasn't brute force, it was physics. Snow became insulation, earth became a thermal battery, and carefully controlled airflow turned tiny temperature differences into a self-regulating engine of warmth. Inuit igluit could hold a 100-degree temperature difference without fuel, while Norse turf houses used the ground's own heat to stay stable through the darkest months. How did ancient Nordic builders turn the cold itself into a source of warmth and create winter homes that rival modern energy efficiency? Part 1. In the high latitudes of the north, winter is not a season, it is a siege. A relentless, months-long assault of darkness, wind, and a cold so profound it can freeze the very air. For millennia, to survive here was to solve a seemingly impossible riddle: how to create warmth in a world made of cold, how to build a sanctuary not from imported timber or quarried stone, but from the very materials of the siege itself, snow and ice. This is the story of an engineering revolution that happened quietly, over thousands of years, in the most unforgiving classrooms on Earth. It is the story of how ancient Nordic and Arctic peoples learned not to fight the cold, but to understand it, to manipulate it, to turn its own properties against it. They discovered that the key to warmth was not a bigger fire, but a smarter structure. They became masters of a forgotten science, a form of thermal engineering that relied on nothing more than snow, ice, and an ingenious understanding of airflow. Two structures stand as the ultimate monuments to this quiet genius. In the far north, the Inuit igloo, a seemingly delicate dome of snow that could maintain a life-sustaining temperature differential of up to 60 degrees Celsius or 100 degrees Fahrenheit between the inside and the outside, and further south, in the lands of the Norse, the turf house, a dwelling dug into the earth and wrapped in a living blanket of sod, which used the planet's own geothermal heat to create a stable, comfortable home through the darkest winters. These were not primitive huts. They were sophisticated thermal engines designed to capture and preserve every precious calorie of heat powered by the simple, inescapable laws of physics. This is not a story about fire. It is a story about insulation, thermal mass, and convection. It is the story of how ancient builders, with no access to modern science or materials, created some of the most energy-efficient homes ever conceived. They learned to heat their homes using the cold itself, a paradox that holds profound lessons for our own energy-hungry world. The Arctic winter is a test of survival that has shaped human ingenuity for at least 4,000 years. Archaeological evidence from sites across the circumpolar north reveals that indigenous peoples developed sophisticated dwelling technologies long before written records began. These builders understood that survival in temperatures that could plunge to minus 40 degrees Celsius or minus 40 degrees Fahrenheit required more than just thick walls. It required a complete rethinking of what a house could be. The challenges were immense. In the high Arctic, winter darkness lasts for months. From November through January, the sun never rises above the horizon in the northernmost settlements. Temperatures regularly drop to -30 or -40 degrees Celsius and can plunge even lower during cold snaps. Wind chill can make the effective temperature feel like -60 degrees Celsius or colder. In such conditions, exposed skin can freeze in minutes. Frostbite and hypothermia are constant threats. And yet, people not only survived in this environment, they thrived, developing rich cultures and sophisticated technologies. The Inuit peoples have inhabited the Arctic regions of Alaska, Canada, and Greenland for thousands of years. The Thule culture, ancestors of the modern Inuit, spread across the North American Arctic around 1000 CE, bringing with them advanced hunting technologies and dwelling designs. The Norse, meanwhile, were expanding westward across the Atlantic. Eric the Red established the first Norse settlement in Greenland around 985 CE, and by the early 11th century, Norse explorers had reached as far as Newfoundland. Both cultures faced the same fundamental challenge: how to create a warm, safe shelter in a land where conventional building materials were scarce or non-existent, and where the cold was a relentless, life-threatening force. Part 2. The word igloo in the Inuit language of Inuktitut simply means house. But the structure it describes is anything but simple. It is a masterpiece of physics and engineering, a perfect marriage of material and form. The genius of the igloo begins with its primary building material, snow. It seems counterintuitive. How can a house made of frozen water keep you warm? The answer lies not in the ice crystals themselves, but in the air trapped between them. Freshly fallen snow is up to 95% trapped air. These tiny air pockets are the key to its incredible insulating properties. Air is a poor conductor of heat, and when it is held in place by a matrix of ice crystals, it creates a powerful thermal barrier. The thermal conductivity of fresh snow is around 0.03 watts per meter second, a value that is actually lower, meaning it is a better insulator, than modern fiberglass insulation. The Inuit understood this intuitively. They knew that the light, fluffy snow was useless for building. The ideal material was the hard, compacted snow formed by the relentless Arctic winds. This wind-packed snow, or siksuk, had been compressed, its crystals interlocking to give it structural strength, yet it still contained enough trapped air to be a superb insulator. When properly compacted, this snow has a thermal conductivity of approximately 0.4 watts per meter second, still an excellent insulating value. The Inuit developed 3 distinct types of igluit, each serving a specific purpose. The smallest was the temporary hunting shelter, built quickly by a single hunter caught far from home in a storm. These could be constructed in as little as 1 hour, and were just large enough for 1 or 2 people to sleep. The medium-sized family igloo was the most common, designed to house a family of 4 to 6 people for weeks or even months during the winter hunting season. And the largest were the community igluit, massive structures that could accommodate 20 or more people for ceremonies, celebrations, and communal gatherings. Some of these community igluit had multiple domes connected by tunnels, creating complex multi-room structures. Construction was a precise art passed down through generations. A skilled builder could erect a family igloo in just a few hours. Using a long knife called a pana, traditionally carved from caribou antler or bone, they would cut large blocks from a suitable snowdrift. The blocks were not random bricks. They were cut in a specific, slightly tapered shape, typically measuring about 60 centimeters long, 40 centimeters high, and 20 centimeters thick. The construction began with a single row of these blocks laid in a circle, usually about 3 to 4 meters in diameter for a family dwelling. Then, the builder would cut a sloping ramp into this first layer and begin laying the second course, and then the third, in a continuous rising spiral. Each new block was shaped to fit perfectly against its neighbors, leaning slightly inward at an angle of about 15 degrees. The spiral was the key to the igloo's strength. It was a self-supporting dome that required no internal frame. The final keystone block was shaped and drop, but the true genius of the igloo was not its walls, it was its invisible engine of airflow. The design was a three-part system. First, the entrance. It was never a simple opening in the side. It was a short tunnel with a U-shaped dip in the middle, built below the level of the main floor. This was the cold trap. Since cold air is denser than warm air, it would sink and pool in this entrance tunnel, unable to rise into the main living area. This simple feature effectively sealed the igloo from the outside wind and prevented cold drafts. The entrance tunnel typically extended 2 to 3 meters from the main dome, creating an effective airlock. Second, the interior was terraced. There was a lower level for storage and sometimes for dogs, a middle level for sleeping, and often a higher platform for sitting and cooking. This took advantage of thermal stratification. The warmest air, heated by body heat, and a small soapstone lamp, burning seal oil called a kullik, would rise and collect in the upper part of the dome where people lived. The colder, denser air would sink towards the floor, where it would eventually flow out through the entrance tunnel. The temperature difference between the floor and the sleeping platform could be as much as 15 to 20 degrees Celsius. Third, and most critically, there was a small ventilation hole, no bigger than a fist, cut near the very top of the dome. This vent was the igloo's exhaust pipe. It served two purposes. It allowed the carbon dioxide from human breath and the fumes from the lamp to escape, preventing suffocation. But it also acted as a regulator for the entire thermal system. As the warm, moist air rose, it would exit through the vent. This created a gentle, continuous convection current, a slow, imperceptible circulation that drew fresh, oxygen-rich air in through the entrance tunnel, up into the living space, and finally out through the top. This constant, slow exchange of air kept the atmosphere inside fresh and breathable without creating a noticeable draft. The rate of air exchange was typically about 1 complete air change every 2 to 3 hours, enough to maintain air quality without excessive heat loss. This system created a remarkably stable environment. The heat from the occupants and the lamp would warm the interior air. This warm air would slightly melt the inner surface of the snow blocks. As this thin layer of water refroze, it would form a glaze of ice, sealing any tiny cracks between the blocks and making the entire structure airtight. The igloo was a self-sealing, self-ventilating, super-insulated shelter, a perfect solution to the challenge of life in the high Arctic. Inside, temperatures could be maintained at a comfortable 10 to 20 degrees Celsius, even when outside temperatures plummeted to minus 40 degrees Celsius or lower. Part 3. While the Inuit perfected the art of building with snow, another group of northern peoples, the Norse, were mastering the art of building with earth. During the Viking Age, which spanned from roughly 793 to 1066 CE, Scandinavian settlers spread across the North Atlantic, from the coasts of Norway to the treeless landscapes of Iceland and Greenland. Iceland was settled by Norse explorers beginning around 874 CE, and by 930 CE, the island had a population of approximately 30,000 to 40,000 people. In these harsh new lands, timber was scarce, but the earth itself was an abundant and powerful building material. The Norse understood a principle that modern green architects call thermal mass. While snow is a great insulator, preventing the transfer of heat, earth is a great thermal battery, capable of absorbing, storing, and slowly releasing vast amounts of heat. The ground, just a few feet below the surface, maintains a remarkably stable temperature year-round, typically around 8 to 10 degrees Celsius in Iceland, staying warmer than the air in winter and cooler in summer. By building their homes into the earth, the Vikings could harness this natural geothermal stability. The ultimate expression of this technique was the Icelandic turf house, or torfbear. These were not simply huts with grass on the roof. They were complex, earth-sheltered structures that evolved over centuries. Construction began with a foundation of flat stones. On top of this, a wooden frame was erected to provide the basic shape and structural support. But the real work was in the walls. They were built from two parallel layers of turf blocks, with a core of gravel or loose earth in between for drainage. These walls could be over a meter thick, sometimes reaching 1.5 meters at the base. The turf itself was harvested with great care. The best turf came from marshes where the dense network of roots held the soil together. It was cut into blocks typically measuring about 50 centimeters long, 30 centimeters wide, and 10 to 15 centimeters thick, and laid in a herringbone pattern. A technique that locked the blocks together and created an incredibly strong, stable wall. The roof was also layered, with birch bark for waterproofing, followed by more turf. A living layer of grass was then planted on top. As the grass grew, its roots would weave through the turf blocks of the roof and walls, binding the entire structure into a single, monolithic shell. These turf houses were often built into the side of a hill or were bermed with earth piled up against the exterior walls. This semi-subterranean design had multiple benefits. It anchored the house against the ferocious winds of the North Atlantic, which could exceed 150 kilometers per hour during winter storms, and it maximized contact with the ground, allowing the house to draw on the Earth's thermal mass. The thick, insulated walls and roof prevented the stored heat from escaping. The R value, a measure of thermal resistance, of a meter-thick turf wall could reach 20 to 25, comparable to modern insulated walls. Inside, the Viking longhouse was a long, narrow building, often housing an entire extended family and even their livestock in a separate section called the fjoss. The main source of heat was a long, open hearth, the langeld, that ran down the center of the main hall, or skalli. This central hearth could be 5 to 10 meters long in a large longhouse. There was no chimney. Instead, smoke from the fire would rise and exit through one or more smoke holes, or liori, in the roof. These openings were often covered with a translucent membrane, such as a stretched and greased sheep's stomach, which would allow light to enter while keeping out the worst of the weather. Just like in the igloo, this simple system created a natural airflow. The rising hot air from the fire would exit through the smoke holes, creating a pressure difference that would draw fresh air in through the doors at either end of the longhouse. While not as sophisticated as the igloo's cold trap, the principle was the same. A constant, slow circulation of air that provided ventilation without creating excessive drafts. The combination of the central fire, the immense thermal mass of the surrounding earth, and the thick insulation of the turf walls created a home that could remain surprisingly warm and stable, even with minimal fuel, through the long, dark Icelandic winters. Archaeological evidence from sites like Stung, a farmstead buried by volcanic ash in 1104 CE, reveals the sophisticated construction techniques used by Norse builders. Part 4. The true genius of these ancient structures lies in an invisible engine that powered them: the stack effect. The stack effect, or chimney effect, is the movement of air into and out of a building driven by a difference in temperature, and therefore density, between the indoor and outdoor air. It is the fundamental principle behind natural ventilation, and both the Inuit and the Norse were masters of its application. It works like this. Warm air is less dense than cold air. In a heated structure, the warm air inside wants to rise. If there is an opening at the top of the structure, a smoke hole in a longhouse, a ventilation port in an igloo, this warm, buoyant air will escape. As it escapes, it creates a slight negative pressure inside the lower part of the building. This negative pressure, in turn, pulls colder, denser, fresh air in through any available low-level openings, such as the entrance to an igloo or the doors of a longhouse. The driving force of the stack effect is proportional to the height of the building and the temperature difference between inside and outside. In an igloo with a height of about 2 to 3 meters and a temperature difference of 40 to 50 degrees Celsius, the pressure difference could be substantial enough to drive continuous ventilation. The result is a continuous, natural, and self-regulating cycle of airflow. It is a gentle, constant loop. Cold, fresh air is drawn in at the bottom. It is warmed by the occupants and the fire. It rises, and then it is exhausted at the top. This engine, powered by nothing more than a temperature differential, accomplished several critical tasks simultaneously. First, it provided essential ventilation. In a small, airtight space, the carbon dioxide from human breath can quickly build up to toxic levels. A fire or an oil lamp consumes oxygen and produces carbon monoxide, a silent killer. The stack effect ensured a constant supply of fresh oxygen and safely removed these dangerous gases. Modern studies have shown that the ventilation rate in a well-designed igloo is sufficient to keep carbon dioxide levels below 1,000 parts per million, well within safe limits. Second, it controlled moisture. Every breath we exhale contains water vapor. Cooking and other indoor activities also release moisture into the air. In a cold climate, this moisture is a relentless enemy. If it condenses on an interior surface, it can turn to frost, reducing the insulating value of the wall. If it gets into the insulation itself, be it snow or turf, it can freeze, turning a fluffy, air-filled insulator into a solid, conductive block of ice. The constant, gentle airflow created by the stack effect carried this excess moisture out of the structure before it could cause problems, keeping the insulation dry and effective. Third, it did all this without creating uncomfortable drafts. Because the system was driven by a small, steady pressure differential, the airflow was slow and diffuse. The cold air entering at low levels would gradually warm as it mixed with the interior air long before it reached the living spaces. This was a far cry from the gust of cold air you feel when a door is opened in a modern house. It was a managed, controlled system of air exchange. The placement and size of the openings were critical. The Inuit knew that if the ventilation hole in an igloo was too large, too much warm air would escape, and the interior would become cold. If it was too small, the air would become stale and dangerous. Through centuries of trial and error, they found the perfect balance, typically a vent with a diameter of 10 to 15 centimeters. Similarly, the Norse builders of turf houses learned to position their smoke holes and doors to work with the prevailing winds, using the wind to enhance the natural stack effect. This was not accidental. It was a highly refined technology, a deep, practical understanding of fluid dynamics and thermodynamics learned through observation and passed down through generations. Part 5. In our modern world, we have come to associate warmth with powerful, energy-intensive technologies, furnaces, boilers, and electric heaters. We build our homes as sealed boxes and then use mechanical systems to force heated air into them. But the ancient builders of the North show us a different path. Their homes were not sealed boxes. They were living, breathing systems designed to work in harmony with their environment. The principles they mastered, superinsulation, thermal mass, and natural controlled ventilation are the very same principles that underpin the most advanced energy-efficient building standards of the 21st century, such as the passive house movement. A modern passive house is designed to be so well insulated and airtight that it can be heated primarily by passive sources: body heat from the occupants, waste heat from appliances, and solar gain through windows. The key to making this sealed environment healthy and comfortable is a device called a heat recovery ventilator, or HRV. An HRV is a mechanical system that constantly exhausts stale, moist air and brings in fresh air from the outside, using a heat exchanger to transfer the heat from the outgoing air to the incoming air, typically recovering 70 to 90% of the heat that would otherwise be lost. It is, in essence, a modern mechanical version of the stack effect engine that powered the igloo and the longhouse. The ancient builders did not have heat exchangers, but they understood the fundamental need to balance insulation with ventilation. They knew that a house had to breathe. They created structures that used natural convection to provide that breath, maintaining air quality and controlling moisture while minimizing heat loss. Their legacy is a powerful reminder that technology is not just about new materials and complex machines, it is about knowledge. The Inuit and the Norse possessed a deep, sophisticated knowledge of their environment. They understood the properties of snow, the stability of the earth, the behavior of air. They used this knowledge to create homes that were not only comfortable and safe, but also profoundly sustainable, built from local, natural materials and heated with minimal energy input. An igloo required no external fuel source beyond the small Qualic lamp, which consumed perhaps 500 grams of seal oil per day. A Norse turf house could be heated through an entire winter with just a few cords of driftwood or peat. In an age of escalating climate change and dwindling resources, the lessons of these ancient thermal engineers have never been more relevant. They teach us that resilience comes not from fighting nature, but from understanding it. They show us that the most elegant solutions are often the simplest, born from a deep respect for the fundamental laws of the physical world. The igloo and the turf house are more than historical curiosities. They are blueprints for survival, written in snow and earth, that still have much to teach us about how to live intelligently and sustainably on a finite planet. Today, architects and engineers are rediscovering these ancient principles. Earth-sheltered homes are being built in cold climates, taking advantage of the ground's thermal mass. Superinsulated structures are being designed to minimize energy consumption, and natural ventilation systems are being incorporated into modern buildings to reduce reliance on mechanical systems. The ancient builders of the North were pioneers of sustainable design, and their innovations continue to inspire us as we seek to build a more energy-efficient and environmentally responsible future. The igloo and the turf house remind us that the most effective technologies are not always the most complex. Sometimes the answer lies in working with nature, not against it, in using local materials creatively, in understanding the fundamental physics of heat, air, and moisture. These ancient structures, built from nothing more than snow and earth, achieved levels of energy efficiency that many modern buildings still struggle to match. They are a testament to human ingenuity and a powerful reminder that sustainable living is not a new invention, but an ancient wisdom that we would do well to remember.